It's a great pleasure to have Pawan Kumar here with us today. Pawan is also an Indian of impeccable taste, but somehow he manages to get it slightly wrong each time. So he also went to the most beautiful places in the world, but because his GPS gets it slightly wrong, he ended up at Oxford Brookes rather than Oxford. And then he ended up at Stanford rather than Berkeley. And Hyderabad, IIIT Hyderabad rather than the beautiful lab here. So Pawan's also done a lot of work in vision, a lot of real pioneering work, but really he's a really smart guy. And whenever I have a problem in discrete optimization, the first guy I'd go and talk to is Pawan. So to tell us more, not about discrete optimization, but a new thing he's developing, self-paced learning, Pawan Kumar.
Thanks to Microsoft Research for actually giving me the opportunity to come here and talk about what is my research program during my postdoc at Stanford. And of course, thanks to Manik for like slotting me in somehow in this jam-packed schedule of really cool vision talks. So the talk has, this is like the only nice illustration, unfortunately, in the talk. It's split into two different parts. The evil part, which is the machine learning aspect of self-paced learning, which is this new concept that we're developing where we want to take intuitions from human learning and put it into machines in order, like, you know, make them learn better. And then there is the good part, which is how will this be useful for several different vision applications. Okay, so the first part is going to be more machine learning. This is joint work with Ben Packer at Stanford, who's a graduate student, very, very serious about life, as you can see from his academic mugshot there. And of course, Daphne Koller, who's my supervisor. Okay, so our aim is that you want to learn very accurate parameters for a latent variable model. And in this talk, I'm going to concentrate on something called latent structural SVM. And I'll get to what it is. It's basically saying you take input vector X, as you do in many learning algorithms. And in this case, our input vector X is going to be, say, this image here, which is a deer walking by. And your output is going to be one of 6 different categories. So you have to say whether this image contains a bison, a deer, an elephant, giraffe, and so on. So it's a multi-class classification problem. And what you also have is, the answer is, of course, deer. What you also have is these hidden variables. And in this case, this motivating example, that's going to be a bounding box of the object that you said was present in the image. Right? So given that object, that bounding box, you can actually extract a whole bunch of features like, say, hog or bag of words specific to that box and sort of do some classification. Okay, so in order to classify, you will actually learn a model that has some parameters W. You're going to take that W and you will take a dot product of those parameters with a joint feature vector of your input, output, and latent variables. So you have, yeah, Alyosha.
Oh, sorry, just in the problem setting. So every image gets to have one class, or
every image? Yeah, this is a very simple data set where every image has only one class. Yeah, yeah. So, you know, typical machine learning stuff. We're not overcomplicating it. Okay, so here's my motivation for self-paced learning. Say I have a student here, right? And I want to teach him. Sorry.
What was the structure?
So the structure in this case for the output, so it's called structured output SVM, and the structure here was just a binary vector that said that deer is equal to 1. So you have a 0, 1, 0, 0, 0, 0, which just encodes the fact that this image is a deer image rather than like a bison image and so on. So it's a very simple structured output in this case. Okay. So say I have a student that and I want to teach him math, right? So one way of doing it would be to just throw all the information in his direction and just ask him to learn something out of it. You tell him what real numbers are and don't wait for him to actually grasp that knowledge. You tell him what imaginary numbers are and then finally give him an Euler's formula. He's going to think that math is for losers. You know. And that's really bad because we have deprived this child of the joys of mathematics, right? So what we want to do is we want to like just really slowly introduce our learner with these concepts. So you first tell him what a real number is. He understands it. Then you go to imaginary numbers, and then finally, when you give him Euler's formula, he will appreciate how big a genius he was, right? Yeah. So that's going to be a good solution for us. Okay. So how do we figure out what these easy examples are, and what the hard examples are, what we should be learning on first, and what we should be leaving till later? Well, one thing you can do is you can use this brilliant tool called Amazon's Mechanical Turk, where some guy will very cheaply label images for you with whatever labels you have. So say, he can sort of label, say, these easy versus hard according to some criteria that he has in his mind. The problem is, as you will keep introducing more and more data, this will become more expensive, right? Now, it turns out at Stanford, expense is really not too much of an issue, but the real issue is that what is easy for a Mechanical Turk is not necessarily what is easy for a machine. And therefore, what you would have to do is to sort of simultaneously estimate or make the machine simultaneously estimate the easiness of the examples and learn the parameters. And the easiness is not going to be a property of a single example that you're seeing. So I give you one image and I tell you whether this is easy or not. That's not well defined. The easiness is a property of a subset of the data set, right? So, yeah.
Isn't easiness a property of the data set and the algorithm?
Oh yeah. Oh, actually, you're perfectly right. So easiness has to be defined on the feature space as well as the model parameter space. So yeah.
But also, also the model, not just the parameter. In fact, that's exactly what I was going to say. I mean, with an SVM, the easy examples don't matter in any case. The only thing that matters are points on the
right. For a convex SVM, the only thing that matters is the support vectors. Yeah.
So there was no point in having shown them the easy examples at all.
True. For that particular one particular case, it's definitely true. Although you could sort of argue that if you first showed it easy examples, it goes to the right parameter space really quickly because it's looking at only a subset, and then it sort of zooms into the harder ones quicker. Maybe there's like an efficiency issue that you can exploit, but we're not going to claim anything like that. Okay, so here's the outline. I'll really briefly describe latent structural SVM and the current state of the art, which is called the concave convex procedure for solving it, and then show you why self-paced learning is different, and prove to you with some experiments that it's actually working in practice. Okay, so for a latent structural SVM learning, you're given a whole bunch of training examples. So you have images xi and ground truth label yi. Once again, images, the ground truth labels are just whether that image contains that particular object category or not. Okay. And you also have this loss function that a user says. So the loss function is basically saying if yi was the correct answer and yi of w, where w are your parameters, is the predicted answer, how happy or unhappy are you with it? So, okay. So what you would like to do is to make the prediction as good as possible, which means you want to minimize the loss in your total error.
What is the loss percentage?
It doesn't necessarily have to be. So for example, in this example, we don't actually use any information about the H, but there are some cases where H's can actually play a part. So predicted latent variables can be included in the loss function if you wanted to. Okay, so this is what we wanted to solve, minimize the loss, but unfortunately this is really non-convex because the loss can be like anything at all in terms of W. So what usually happens is people minimize an upper bound on this. And the upper bound looks something really similar to what you have in your normal SVM, except now you have these latent variables. So what you do is you say, I'm given xi and yi, which are the ground truth. Now, the best hidden latent variables that are consistent with your ground truth have to be better than absolutely everything else. If they're not, then I'm going to add a penalty and I'm going to minimize that penalty, right? So it's still a very nice and intuitive objective function that you're trying to minimize here. Okay, but it's still non-convex. Although it's a part of what we call DC programming, a difference of convex programming, and it turns out you can actually do this really efficiently by this algorithm called convergent convex or constrained concave convex procedure, or CCCP for short.
Very unfortunate.
Why is that?
It's USSR.
Oh, is it? Okay. Here's another reason why we should all move to self-paced learning, I guess.
Pawan, sorry, I couldn't see the slide. Why is this not convex? What makes it?
Oh, there's a maximization over your latent variables h here. So if you were to take that up onto the objective function, you will get a minimization of a minimization, and that becomes. Okay. So CCCP is so that's what this is what CCCP does. You start with some initial estimate. You figure out according to your initial estimate what is the best guess of the latent variables that you were not able to observe, right? And then fix that, and then solve a convex problem. So that max guy is gone because the max has been fixed using the previous estimate of my parameters, and I'll keep doing this up until I converge, right? So fairly simple algorithm again. But the problem with it is that it is actually looking at all these samples simultaneously. So if you go back to that boy, he's actually trying to learn all of math at the same time, which is not going to be a good idea. Or in my case, if you basically have an initial parameter which gets some of the Dier's bounding boxes right and some of them wrong, you're actually going to try and learn a Dier from those wrong models as well, and it's obviously going to lead you to a wrong local minima. Okay. So once again, just to reiterate, what we would like to do is to start with the easy examples, hopefully corresponding to the ones where the bounding box was actually correct, and then gradually introduce more and more examples that become for which you can find the bounding box correctly.
And again, I'm still trying to play catch up. So you have a convex concave optimization problem. You need to use DC programming to solve it, but that will converge, but not to a global optimum.
That will converge not to a global optimum, and our algorithm, which I'm going to describe, is also a local optimum algorithm. But it turns out that in a lot of applications, our local optimum is better than their local optimum, because we're looking at a subset of images first and then expanding our set of images as we go along.
Then this argument really does become important. So if it were a global optimum, then it really doesn't matter whether, or in some cases won't matter whether you show them the easy examples or not.
Yes.
But now because you're going to converge to a local optimum, this becomes very important.
Exactly. So this is more an optimization issue than just changing the objective. The objective remains the same actually. Yeah. Okay, so self-paced learning turns out to be a very, well, in terms of implementation, a rather simple extension for CCCP. So you fix the first stage, which is you have some initial estimate of your parameters from which you impute your latent variables, fix the latent variables, and now you're going to solve this problem which updates the parameters, right? The last set of equations there. And this is where we want to restrict ourselves to a small subset of the examples. Okay. So we have this, and now I'm going to introduce a set of indicator variables, right? Vi is 0 or 1. 0 means I'm not going to be bothered about this example because Vi will multiply with the loss for that guy, and if it's 0, then it doesn't matter. And if Vi is 1, then those are my easy examples. So because I'm minimizing, I will choose those Vi is equal to 1, which are actually easy examples. Right. Obviously, this has a trivial solution that you put all the VIs to 0 and you're done. So what we do is we introduce this penalty that says you can't have everything as 0. So for every single one of those VIs that is 0, you have like a penalty of minus 1 by k. Or actually, for every one of the ones that are VIs that are 1, you have a reward of minus 1 by k. Okay, and k is called is the self-paced learning weight, right? So you basically start off with a really large k that's going to ignore your hard examples, and then you will slowly start to increase it. And in our method, we basically just divide it by a constant factor. And then you keep doing this up until a point of time where you can start to consider your entire data set.
So your change in K could be interpreted as some kind of learning rate to adapt to different.
Yes, it is that, yeah. Okay, so this is a mixed integer program because you have W's that are real variables, VI's that are zeros and ones and so on. So I'm going to relax it to lie between 0 and 1, but this is a tight relaxation. So the optimal solution for this guy is going to have integer solutions for V. Hand wavy explanation is that it's just a linear function in V, so you're not losing out on anything. Okay, but it's a biconvex problem. Now there are lots of people who have done biconvex optimization. Some do it locally, some do it globally, but with a lot more time. We're going to do it locally because time's actually really an issue for the later part of the talk. So
It's not convex jointly in W and V.
yeah, but it is convex. So it's convex in W's when you fix V. It's convex in V when you fix W. And so you can actually do this alternating convex search where you fix one, estimate the other, and then go back and forth until convergence.
By the way, but that is not even guaranteed to converge to a local optimum. I can construct functions where this will just converge.
Right.
And it's optimal in the sense if you fix one variable, then you are at an optimal.
Yeah, so it's what we call the move space optimality, right? Like so within the move space search, move search space, it's
not jointly optimal in both variables either. It's not even a local optimal.
Agreed. No, I agree. I'm completely agreeing with you. I'm saying this is the term for it is like a move space local optimum, where it's conditioned on the moves that you were making. The move being you fix one and sort of and update the other. So for any given V, there won't be a better W, and for any given W, there won't be a better V. That's the only guarantee that you have with this. But if it works in practice, then there's no need to actually go and do something more complicated. And I can't. Sorry. Well, no. I mean,
You say it works in practice.
Yeah.
That means what? You've done a few experiments and so on and say it works. But
Yeah. So
and you say theoretically, Manik says that it's not even guaranteed to get local optimum.
that's true.
I believe that it actually works.
I mean, I believe in sort of just empirically, like looking at results and then figuring out whether this is a good enough algorithm or not. Obviously, you could have done something more complicated. There is something called a global optimization search for biconvex problems that will guarantee global optimality, but it will take a lot longer. And it's just a trade-off between time and accuracy in some sense. I guess if it turns out that in your experiments it's actually not doing a good job and you're not satisfied with the accuracy, then you can go and invest this thing. But it did a pretty decent job for us. So, sorry. Well, I mean, to be honest, I can't believe that I'm saying this right now because my entire graduate studies life, I strive for global optimality and for optimization and stuff. But sometimes you have to realize that it's the practice that actually matters, not the theory. Okay. Sorry. So for the examples that I'm going to show for the first part, it's actually pretty small, so a few thousand. But for the vision application, the size of the W is like about 200,000 parameters, maybe around, so that high.
But I think the more important thing is what is the size of V, right?
Size of
The thing that makes it difficult. I think you called them V or H, or I couldn't see your slide.
the latent variables, yeah, the H's, yeah.
And that is equal to the number of training data points, so that can go to be quite large.
Yes, and its dimensionality actually varies like a lot between different examples in our later setting. So, okay, so this is basically just self-paced learning. You start with some initial estimate, you get your latent variables, and then you choose a subset of your examples according to some weight k, and then you keep increasing this k until you can start to include absolutely everything. So, okay, so why does this work? So I'm just going to show you the object detection example here again. So here are some typical results. Blue rectangles means that that example was considered while you were training during that particular iteration, and red means that it wasn't considered during training. And these aren't hand-picked examples. These are what we observe in practice for this particular data set. So you can see that even though we didn't tell the algorithm anything about what is easy and what is hard, it sort of figured out that the ones where the bounding box is sort of off the object is actually a hard example, and therefore I shouldn't be using it right now. I can use it when my W's get so refined that I can nail down the right bounding box in my image. Right? So I proceed further. It sort of wiggles it around again because the parameters have changed, and then eventually, like you can see for the first and the third example, it's now found the bounding box that it likes, and so it's going to start including it in the optimization, and then eventually it's going to start including absolutely everything. And this is going to be a lot better than CCCP, where it just got stuck. Right? You gave it a bad example and you said this is ground truth, and it learned that that was ground truth. So it just got stuck with these bad bounding boxes. Okay, so here's some quantitative evaluations, I guess. We had 4 different folds for the standard mammals data set. In each of them, the objective function value, which is really the point of this thing, to get a better objective function value, decreases. And when that corresponds to like a generalization error, you get some improvement in the test error as well.
Sorry, I
Yeah.
keep interrupting. And I feel bad
No,
for it,
please.
but conceptually, now when you say you have 200,000 parameters, there's something that could go wrong, right? You have very few examples now because you're starting with only the easy ones.
Yeah.
So you've reduced your data set.
Yeah.
You could overfit very badly, and you could end up in a region of the space that's very bad. And
It's
then getting
true.
out could be very difficult.
It's true. So the one parameter that you have to be pretty careful about with these things is the value of k at 0 iteration. So you need to make sure that like you play around with that a little bit as you have to with any learning algorithm. So and include enough number of examples where you don't get pushed into a bad local minima. So there is
What about the C parameter? Do you change that simultaneously, which says how much?
So it's true. So I got told off by Daphne for not doing that actually, but it's the obvious thing to do because C's will determine how much complex you think your solution is going to be, and so you can actually anneal that as well as you go along. But yeah. Here's some other. This is like a really boring application. Which sorry.
Can you give an example? What is
H
H?
is the bounding box for the object. So the ones that I'm showing you there. So that hasn't been given to us. So the boring MNIST data set, which machine learning people just love. Once again, you do really well in objective function value. So in this bottom curve here, the higher you are, the better self-paced learning is doing to CCCP. So you have a few examples where it sort of goes wrong, a few examples where it sort of goes up, but it's within like it gives you some improvement in overall accuracies. Once again here and here, and then this one example was where it sort of really worked well. Right. So the thing with CCCP is that it's actually a pretty reasonable algorithm, but sometimes when it goes into a bad local minima, it just stays there and gives you really bad results. And we found that self-paced learning actually was able to get rid of those kind of situations where like CCCP just got stuck. Okay, so this is more of a CombBio experiment where you have a whole bunch of DNA sequences. DNA sequences seem to tend to have these motifs in them, which are these repetitive patterns that govern its characteristics. So the presence of those motifs can indicate whether it binds to a particular protein or not. The absence will indicate that it's not likely to bind to a particular protein. The position of that motif is unknown, so we sort of model that as a latent variable here. So here's another like interpretation of what the imputed latent variables look like. I'm showing you the average Hamming distance over all the motifs that I found in my DNA sequence. Now, because these were supposed to be repetitive patterns, smaller the value of the distance between them, the more consistent they are with each other, right? So what happens with CCCP is that you start off at a really high position, that red curve there. So right here. and then it starts to do something slightly better, so it pushes it down a little bit, right? Whereas what happens with self-paced learning is that you start off with really easy examples. So it turns out that the easy examples, once again, have a nice interpretation that the motifs are actually kind of consistent with each other. And then it sort of starts to include more and more difficult examples, so the blue curve is rising up, right? So it finally gets to a point where it will consider absolutely everything and then starts to push it down. And usually it will push it down further than what CCCP was doing. So the final average Hamming distance is actually a lot better for self-paced learning than it was for CCCP. Once again, especially in a few cases where CCCP really starts to get stuck, you can see there's like a very significant difference. So in terms of like your objective function value, you have 4 folds in which CCCP did rather well, but you have a 5th fold where it just got stuck, right? And that's when self-paced learning was able to recover. And in fact, when you look at the test errors, for the last fold, CCCP gave as bad an accuracy or as much of an error as chance. So it was 50% accuracy, really. Whereas SPL gives a pretty decent performance. One final application that we tried it on for our machine learning paper was noun phrase co-reference, where you're given a document and it has a whole bunch of nouns in it, and you want to figure out which one of the nouns are referring to the same person, right? And this has a latent SVM formulation which was given by Yu and Joachims. We just took their method and we applied our self-paced learning algorithm to it. And once again, if you look at the objective function, we tend to do a lot better than CCCP for most of the cases. So these curves, once again, if they're above this black line, that's good. If they're below, it's bad. So there's like one example where we actually did far worse, but overall we were actually a lot better. These are again losses for different C values. If you were to sort of pick the best ones, then we have some improvement there. Yeah.
So can you go back?
Yeah.
I might be asking a complete, no, just to the slot, one further, where you had. Now these are iterations on the X.
Oh, so in the x-axis, I'm showing you different C values. C being the relative weight of the loss to the regularization parameter in my objective function. So yeah, people tend to basically run it for all sorts of different values of C and then pick one up using validation, cross-validation basically. And of course, for test loss as well, we see self-paced learning is actually doing a pretty decent job. But what is nice about all of this is that the latent variables that we were imputing seem to have a lot more intuitive meaning than the latent variables that you were getting from the other state of the art till now. Okay, so just to summarize, we have an automatic method. There's nothing that we are actually sort of giving to the learner that wasn't present in the state of the art, other than the fact that we need to sort of consider fewer examples first and gradually introduce more examples. Instead of concave convex procedure, we have a concave biconvex procedure, but that's not a big issue. It sort of generalizes to other latent models as well. So you can do expectation maximization in the same way, right? So you marginalize out your latent variables, you get some objective function that you were maximizing in the M step, and in that M step you can say I'm going to use only a few examples that I'm actually confident about, and that tends to do better than your vanilla EM algorithm. Okay. The details of all of this are in our paper that was just published in NIPS 2010, and I welcome you to go and look at it. We're going to make the code available as well, so you can play around with it. Okay, so that takes care of the actual like machine learning aspect of self-paced learning. So just to emphasize that I'm going to now shift gears a little bit and talk about a vision application. I'm actually going to change the presentation. So that means I'm no longer a machine learning person. Okay. So okay, and this is work that I've done with a couple of undergrad and master students at Stanford. So yeah.
Can I just ask a probably very naive question?
Right.
does it make sense to compare these methods to very standard methods like AdaBoost?
In terms of accuracy, definitely.
Yeah.
But
And so-
the reason why we weren't actually looking at that was because it is more about solving a particular objective function value. And what we wanted to show was that the other method that was solving the same objective value was doing.
Yeah, I understand that, but is there
But,
some-
of course,
is there some advantage for some
so,
particular problem to solve that?
Well, the original paper compared it with a lot of standard classifiers, basically. And so we didn't feel like that was our contribution. So you and Joachim's and well, maybe Felgenschwab didn't compare it with anybody else, but you and Joachim's compared with a lot of different people.
Okay, so it's already been established.
Yeah. So CCCP itself was doing really well, but yeah. Okay. So yeah, this is work that I've done with my undergrad Haitham, my master's student Dan, and of course Daphne, who was the big boss. And okay, so the aim of this work is you're given an image, and now you want to get a segmentation model for it, such that if you use that model, you get a pixel-wise segmentation of the image. So here you can see that the output says here's a car here. These are trees, the sky, road, grass, and so on, right? And so in this talk, I'm going to use 27 different classes that are shown there. Okay. It's going to be slightly different from, say, the Pascal challenge because we're not going to use generic classes. So there'll be no generic foreground, no generic background. We're going to label every pixel as a specific class, specific in terms of say grass instead of generic background or like car instead of generic foreground. But that's not really a major issue. It's just that I don't like looking at these generic classes. What is more important to me is that this work is going to try and train using both strongly supervised data and weakly supervised data. So it's going to try and learn from as many different amounts of data as you can possibly find for free on the internet, right? So just to emphasize that point, mostly in vision what happens is some people look at strong supervision. So you have the Pascal challenge where you're given the pixel-wise segmentation of an image, or you have like the Stanford background data set where you're given again, pixel-wise segmentation, and then people use supervised learning algorithms and so on to actually come up with a segmentation model for a new image, or a segmentation for a new image. The other type of people are the ones who will basically say, I'm going to use weak supervision because I'll have lots and lots of data for it. So I have, say, bounding boxes of objects, or I have just image level label that say, here's an image, there's a car in it, I'm not going to tell you anything else. Somehow learn what a car model is by looking at what is common across all these images. So, and there is this great divide between these two types of people, right? So to use one of Daphne's phrases, this is what she calls one hand tied behind the back vision. So you either say, I'm not going to use all the data that is available to me, I'm just going to use the strong supervision, or you say, I'm just going to use the weak supervision, I don't really care about the strong data at all because I want to show how well I can do with very little information in my data set. Okay, so we want to get away from one hand tied behind the back. We want to combine all these data set and go from data in vision to data for vision, right? If it is out there, then use it. There's no need to solve a problem that doesn't exist. Okay, so the types of data that we are looking at is, once again, we have the Pascal segmentation data sets where you're given the segmentation of every object, every foreground object. You have the Stanford background data set where you're given the segmentation of every background pixel. And then you have these bounding boxes of objects where you have somebody has gone ahead and drawn a bounding box around whatever object he was interested in, so a bus or a car or what have you. And these are literally thousands in even say the Pascal detection challenge. Now what happens when the challenges are run is that these images are just ignored by the people who are participating in the segmentation challenge. And what we would like to do is sort of use the power behind even a simple annotation like bounding boxes to get a better segmentation model. So like I said, it turns out that if you were to give this kind of an information, most of the methods have actually just shown like, what happens if you use 200 really controlled images of this sort. We don't really know what happens when you use thousands of images of this sort to learn a big segmentation model. Then you have image level labels. Once again, it's basically just saying you have an image and you have just a label for it, no information about where the object is and so on. And this is an even bigger question mark, of course, because now the bounding box information has been taken away from you. So even though this talk is not going to address this next type of data, I'm just going to put it in because I'm going to talk about what we think can be done. So this is noisy data from Google. So I go to Google image search, I type in cars, and I get a whole bunch of data where some of them just don't contain car, or some of them contain like, this Disney Pixar cars here, and we probably don't want to use them for learning. So you need to figure out like which ones to use and which ones to not. Now, obviously, if you could do that, then this opens up the millions of images that are actually out there in the web for you. Like I said, this is a bit too big a question mark for us right now, but I'll sort of come back to it at the end. Okay. So I'm going to describe my region-based model for which I'm going to use all this diverse data, but it's not specific to this particular model. I can actually use my general idea for any type of segmentation model. And then I'll formulate the problem, show you exactly what kind of results we get. Okay. So the model that we have actually tries to take an image pixel, take the image pixels here, and then just group them up into a whole bunch of regions. Now regions are just nothing but a set of consistent pixels, right? And the reason why we want to use regions is because these actually tend to give us the features that are more discriminative than just taking a pixel, taking a patch around it, which may or may not include the object that you were considering, and that might actually screw up like your learning. Right? So you want to group the pixels into regions and label the regions instead of labeling the pixels itself. And you have this object models driving the segmentation. So this is kind of similar to my OptCut work where this object model is going to say, I found a car here, so try to make sure that the segmentation that you're trying to get has a car in that particular area of the image. So if I were to do inference on this model, I expect to get results of this sort. Okay. So my problem formulation is going to be the following. So I have an image that has been given to me, and I also have some annotation, some incomplete annotation Y that has also been given to me. So in this case, I have specific foreground but generic background, and then my latent variables are going to be these variables that will complete the annotation for me, right? So every generic background pixel here, I've been able to figure out what the specific background for that is by introducing these latent variables. Now, given these three things, basically the image and the complete annotation, I design a joint feature vector for my model, which will have all sorts of different features in it. Region features that we know are sort of robust to noise. You have detection features, which once again say if a detector finds a car, then you want to segment a car in that particular area. You have some pairwise contrast terms, some pairwise context terms that say cars are usually on roads, boats are usually on water, and so on. The details are really probably not that important. As I said, it works for any model at all. But what is important is that we would like to now learn a bunch of parameters for our model, such that if you were to say maximize the score for those parameters, you get the right answer for your images. Okay, so this is once again our good friend latent structural SVM, and so I can just use some overlap law score. This is like the standard score used in Pascal, and I can then train it using self-paced learning, right? Because I know that actually works pretty well. So self-paced learning, like I said, has two steps. First step is that you figure out what your latent variables are given your current parameters, and the second step is that you solve this convex structural SVM problem. So let me just concentrate on the first step, which in this case I'm going to call annotation consistent inference. So I'm given an annotation for an image, and I want to figure out the latent variables that are consistent with my annotation. So if a pixel has been marked as generic background, I can't label it as a specific foreground. That's basically all it means. Right? Okay. So the inference for my model needs me to group the pixels into regions, right? So which is a very, very complicated combinatorial optimization problem. So I'm going to use a much simpler strategy where I will make use of the fact that vision people can give me a much smaller set of possible pixel to region labels, right? Which are basically these over segmentations that you get from, say, mean shift or like global PB or what have you, right? So I have some regions right now, and I have a whole bunch of these over segmentations here. I'm going to take every one of those segments and merge and intersect them with every one of the regions that I have and make this very, very big dictionary of regions, right? It's going to be huge. It's going to have overlapping regions in it. It's going to have, it's going to have enough number of regions that it can actually cover the image that I have, right? From that big dictionary, I'm going to choose regions that satisfy two properties. First is that no region should overlap with any other region that has been selected. And the second, of course, is that it should completely specify the entire image. Now, this is like solving a jigsaw puzzle where the pieces are actually far more than you would have actually required. Right? Okay, and I'll keep iterating this until I converge. So that's basically my strategy. And the selection of the regions turns out to be a much simpler combinatorial optimization problem that I can solve. It solves a linear objective function over a polytope that I call select of D, where D is the dictionary. So, okay, I've included this slide only because I don't want to. It's not because I want to explain what select of D is. It's just that it's just to make the point that inference is at a stage where if you get to a point where you have an integer program, or if you get to a point where you have a combinatorial optimization problem, you convert it into an integer program, you figure out what its relaxation is, and you just solve it using a super parallelizable dual decomposition algorithm. And so this is an area that is just mature. You can just take it and start using this now, right? So we took it, we started using it, and what we achieved in the end was a simultaneous region selection and labeling. And this is very different from what people usually do, where they fix the regions using, say, some mean shift segmentation and then select its labeling. Now, the problem with that, of course, is that you don't know whether your regions were good enough or not, right? You want to get a big candidate of regions and then choose from them by minimizing just one energy, rather than choosing some other energy for selecting, some other energy for labeling, and so on. Okay, so here are some examples for these generic backgrounds. I have an image for which I had been given an annotation where these checkered marks here are basically just generic classes, right? So now I want to fill these guys up, and I want to fill them up with of course, the right thing. If it's not the right thing, I'm going to rely on self-paced learning to say that I'm not going to select that particular example at that time, so which is that red bounding box around the image. So at iteration 1, it just finds a few examples that it's happy with, and it sort of discards the rest of the examples. And then we keep going along, and it sort of tries to figure out that what you were seeing in the middle row was actually a cow and not a sheep. Once it's figured that out, it includes it. So actually that's confusing, because it doesn't know that it's actually done the right thing. It just knows that it's been able to include it now with sufficient confidence. And it just turns out that it has an intuitive meaning. Right.
Now, in your simultaneous region selection and label,
Yep.
we look at the cow.
Yep.
Do you do some implicit region grouping there, or do you really just select?
So what we do is that we take our current set of regions, and then we just group them with segments, and we group them with themselves, and we just create a candidate region. Now, just because we have a candidate region that is a group of some regions.
Over-segmented regions,
Yeah.
you take them and group.
You group them, you split them, because
Merging and splitting.
yeah, we do merging and splitting, and then we choose only a set that is sufficient for this task. This, by the way, goes back to like the whole vision, direction of how do you use multiple over segmentations in order to do your task. So yeah, and I think this is a nice way of actually looking at it. You don't want to use multiple segmentations if you can actually get one segmentation that is correct. You want to use multiple segmentations to get to that one segmentation, right? Okay, so once again, this is what happens. Okay, so I also talked about bounding boxes, and what we do with bounding boxes is we take our LP where we were selecting the regions, and then we say when you're labeling the regions, make sure that every row and every column of that bounding box has been covered by the object class that it was supposed to contain, right? This is just using the fact that bounding boxes are usually pretty tight. By tight, I mean that every row and every column was actually containing a pixel that belonged to that object. And this turns out to be, once again, a really simple linear constraint, and then we can just relax it and find the solution, right? So you have, say, this image here where so you have a cow and a bounding box for that, and here's a completion of that cow. So the green pixels here are the cow. The white pixels are basically void. So the things that I don't cover with the object class that I have right now, I'm not confident about, so I'm just going to say I'm going to not label them, right? And then obviously what is not inside the bounding boxes is, in the Pascal case, for example, is a generic background. So what I've done is I've taken bounding box data and I've reduced it to my previous problem where I had generic class annotations, and now I can do the same thing again. So I can actually learn Alyosha.
So, okay, so for stuff, this kind of a, looking at the best segmentation, picking the best of the kind of, that makes sense. For things that are labeled, like this airplane, you have this detector which basically tells you what is the right segmentation. What about for things that are not one of the 20 Pascal classes? There are plenty of things like that, right?
So could you repeat that? What happens if I have an image that is not one of the 20 Pascal classes?
No. What happens if you have an object in an image?
That is
not one of the things, like
right. Okay, so
a cup. A cup is not in Pascal.
Right.
So the problem with this region-based thing is that half a cup is just as good as a full cup, right?
Right.
There is no way it doesn't. The region-based stuff doesn't know that it needs to grow, right?
Well, it's true, except like in our case, actually, we don't have that problem because we're sort of assuming that we're in an environment where we don't have a generic class, right? So it needs to be an object that we've seen before, that we've trained on before.
So you're assuming that apart from the 20 Pascal objects,
and
everything else is stuff, everything else is texture.
Everything else is background, and some specific background as well. Yeah. So typically we see like these interior objects can tend to get labeled as building, because building is like this generic class that we sort of end up using anyway. Okay, so once again, I'm going to rely on self-paced learning to prune out the examples that have some noise in it. And so at iteration 1, it's going to choose that cow image or at the top because it's pretty confident that it's got it right. And then this guy here, you can see the sky is being labeled as something else. And in here, the trees are getting mislabeled as grass and so on. So you keep, you iterate over your self-paced learning, and eventually it sort of figures out what the mistakes are, and it starts to include them back again in your training example. So once again, these are not hand-selected examples. These are examples that we typically find. The things that self-paced learning says are not to be used turn out to have this like nice intuitive interpretation that in fact the inference actually sort of failed a little bit there, and we didn't get the right object the right segmentation. Okay. Finally, we have these like image level labels where you just have an image and you have the presence or absence of an object category there. That once again turns out to be a really simple linear constraint that I add, which says that image has to contain that particular object, right? So some of the pixels in that, or some of the regions in that image have to be that particular class. The rest I can sort of, say are void. I don't know anything about them. That information is not present. So, okay. So, okay. Here are some quantitative results. So we took the Pascal VOC 2009 data set, and combined that with the Stanford background data set. So you have Pascal where you have generic background, and you have Stanford where you have generic foreground. And if I combine them, I get a problem that is a 27 class problem rather than a 20 or a 7 class problem. I split these things up. I use a validation data set to sort of early stop my self-paced learning. So I sort of took the VOC train val thing and sort of used a bit of a validation data set in my setting. But of course the test images are sort of fixed as they are in VOC. Okay. And the baseline that we used was this really nice closed loop learning method that we had developed for exactly this model in the previous year. And obviously you want to beat what was the best for your particular model all the time. So that's basically the comparison. So the bar graphs that I'm showing are the difference between our method's accuracy and CLL's accuracy. So the higher up the bar is, the better. If it's below the 0 thing, then we have actually done sort of slightly worse on it. And as you can see, the improvement is nicely across the board pretty much. Right? So out of the 21 classes that Pascal's looking at, 4 of them, our method was actually worse than closed loop learning, but for the rest of them, it was actually better. Right? And overall, of course, it was better as well. And the same thing was true for Stanford background data set. We overall do better than the state of the art. Okay. Now I took the Pascal VOC 2010 images, and I chose from them all the bounding box images that people were not using. Now, the reason why I didn't use VOC 2009 bounding box images is because I'd use them to train my object models that sort of drive the segmentation. So I didn't want to overcount the data.
2009 is included in 2010.
Yeah, so these are only the new 2010 images, which is why there are there are only 1,500 of them. So, but obviously these kind of images are there in ImageNet as well, so we can actually get more. Right. So once again, I'm showing you both the results now. Just the 2 data sets combined, the segmentation data sets combined, and the new bounding box data. So you can see once again, you get pretty much across the board improvement over the previous LSVM, and overall the accuracy improves as well for both Pascal and Stanford background data set. So there are a few problems. Actually, this overlap score has is an intersection by union thing. So if I had a huge prior on, I'm going to label everything as say mountain or something, it actually ends up boosting that performance artificially a little bit, so that when you start doing better for the other classes, it sort of, it pushes it down. I think that's true for most of the measures that we actually use in segmentation. And I don't know how to fix it other than saying, I would like to see chamfer distances between predicted and true labeling, and that might actually be a much better and a more useful measure for segmentation accuracies. Yeah, so I'm almost done. So this thing was being done for a particular submission, which was looming on us. So we had to restrain ourselves to about 1,000 image level labels, which we got from ImageNet by just randomly sampling. There was nothing, no bias here about how it was sampled. So 1,000 really turns out not to be enough to get a huge boost. We still get, once again, pretty much across the board improvement, but the overall improvement is just like 0.5% for both the data set. 0.5 is actually, I think it's pretty good, and if there were multiple folds for these data sets, especially Pascal, then maybe we could have shown statistical significance, but turns out that Pascal sort of likes to hide its test data set for very good reasons, so we can't actually do that. Okay. So some example images. I've handpicked these, obviously. These are like super nice images, so I'm going to skip them. I want to make a point. So to conclude, just to look at the data that we can handle. Of course, if you have a generic background, then you can do this really easily by just saying my latent variables are going to fill the generic background with a specific background. If I have generic foreground, my latent variables will fill it with specific foreground. If I have bounding boxes, then I'm going to use the constraint that the bounding boxes are tight, and I'm going to get completed segmentations. So that question mark, I think, disappears. You have these image level labels where the only information you have is the presence of an object. So you can use that in order to complete the segmentation. So we get rid of that question mark. But we had this big one here, right? Which is if I go to Google Images and I type something, how do I use those images? The problem with that is I have two problems. There is the noise problem, because Google will not return all the car images to me unless, Manik obviously does a great job and solves that problem for us. But if he doesn't, then we're going to hope that self-paced learning is actually one of those things that will allow you to filter out the noise. The whole idea is that you're not supposed to use the images that have noise in it, and that's what I was showing you in my intuitive explanations for the latent variables. And of course, you have the size problem, and that means given millions of images, will you ever be able to do something sophisticated, or will you have to resort to very silly algorithms of just doing say efficient nearest neighbor on by learning no weights and stuff at all, which works by the way, but maybe this will work better. And once again, I think the solution to that really is self-paced learning. And the reason for that is that when you're teaching a child, once you've taught him real numbers, the next time he comes to you, you just remind him what real numbers are, then you tell him what imaginary numbers are. The next time he comes back to you, don't say, oh, by the way, do you remember what real numbers are? You assume that he has learned it. The model has absorbed that information, so you can drop those images now. So in that sense, the effective size of the data set over all the iterations is actually pretty small. And I think there's hope to actually use this concept in order to learn parameters from lots and lots of images instead of just doing something simple.
In a way, what you're really proposing is to amount some regularization by analyzing the data.
Sorry?
You're proposing some form of regularization by looking at your data.
Yes. Yeah, I mean, by effectively reducing the size of the...
Regularize the problem by pushing stuff that's difficult out of
Yeah.
the learning.
Yeah. No, well, not completely out of it. I'm gonna bring them back when I'm confident that they'll be useful. Alish.
So philosophically, this is kind of reminds me of this KNN SVM thing.
KNN SVM's thing.
KNN.
Remind me again,
So this is Jitendra's baby, where he first does the KNN to basically focus on the region of the space which is interesting.
Right.
And then in that region, basically of hard examples, then he does the SVM.
Actually, I
Right.
think I totally disagree. The philosophy over there was to get get classification accuracy better. The whole guiding thing is this area of the space is hard, let's focus on this.
Right.
Pavan is doing it purely from an optimization perspective. And actually from the optimization perspective, I think the results are really against you in the sense of theory, right? So if you look at the theory, the best rates of convergence for stochastic gradient descent are exactly the same as the rates of convergence for batch method.
But this is not talking about rates of convergence, right? This is...
So if you're saying that you will converge faster.
Well, no. I actually said that there might be something to be said about that, but the whole claim is that it will give you a better objective function value. It might actually not do it faster. In our experiments, it took twice as long to do self-paced learning than it did for CCCP. And I'm happy to put twice the amount of effort in terms of computation to do that. But it's fundamentally different in the sense that KNN SVM seems to be saying, let's focus on the hard examples, let's nail them now. Whereas what I'm saying is, let's use the easy examples to learn more about our world, and only when we know a lot about our world will we go and look at those hard examples. So I think philosophically they're different.
Well, in KNN SVM, the KNN is the easy examples, right?
Right.
And the SVM is the hard one, so that's the
Right.
separation. But I see what you mean, that you don't really learn anything with
Right,
KNN
right,
SVM.
right. Aaron, sorry. Sort of.
So extending the analogy, so you say that if you show data story, harder data later.
Yeah.
Is it also that should we be building the model complexity simultaneously?
Yes. So you're ruining my ICML paper, but yes, sir. Okay, we're doing that right now. So in our setting, the complexity is determined by a kernel, and you have a complexity term on the kernel, and then you sort of anneal penalties on the complexity, so that when you see harder examples, you can learn more complex kernels and do better. That's like an extension of what Andrew was saying, where you sort of anneal C as well, right? So you make it more complex. But yeah.
Your harder examples are also going to be scattered all over your decision surface, right?
Well, for a linear SVM, basically, it's actually like the ones that are closer to the margin and stuff, right? That's what a hard example is.
You don't have to sort of split those into groups.
No. Andrew?
I wanted to try and get some intuition on why this would help with the noise problem.
Right.
I've got a well-formed question, but say I was doing the classic ransack between straight lines to noisy data.
Right.
So, and you want to ignore somehow you want to find the points which lie on the line and
Oh, I think maybe I'm talking about something so much more simpler, where you have your self-paced learning telling you which examples to learn from. You learn, you go to a validation data set that tells you whether your generalization error is good or not. And as soon as you've introduced noise, your generalization error falls down. So stop there. You say, I don't want to use these examples because they're either too difficult or noisy. I mean, for me, it's the same. So there's a nice enough. There's a very, very simple procedure for that. Really, the only problem is size. Yeah.
So, are there any more questions? Otherwise, let's thank Pawan.
Anyway, we want to thank Pawan